Okay, so this is again going to be about list decoding and try to limit the background, etc. Focus more on the proof. Let's start. So let's say we have a rate R code. List decoding radius or list decoding capacity is 1 minus r, which means that such a rate R code cannot be decodable to a radius beyond 1 minus r. Or if we have Hamming balls of radius more than 1 minus r, then at least some ball will have more than polynomial number of or exponential number of code words. And the question is, can we get close to this? And random codes do very well. If you take a random linear code of rate r over large enough alphabet, then you can get list decoding radius to be 1 minus r. And for a while, we did not know how to get explicit codes with this sort of property. And the main result here that was first to do this was Guruswami Rudra 2006, which used the folded Reed-Solomon code. And they were decodable up to radius 1 minus r minus epsilon for any epsilon that you want. And these were based on just modifying our usual Reed-Solomon codes by folding them together. By folding, I mean that you think of maybe 3 coordinates at a time and call them a single new symbol. The list size here has to be polynomial for it to be decodable up to 1 minus r minus epsilon, and the precise polynomial was roughly n to the 1 over epsilon. This is not ideal because the random constructions actually achieve 1 over epsilon. So there's a big gap here. And then there's been a long line of work trying to reduce this list size. So again, Guruswami in 2011 showed that the list is contained in an affine subspace of dimension 1 over epsilon. So this immediately implies a list size upper bound of q to the 1 over epsilon, because you can try out all possible affine combinations. And q roughly can be taken to be n in these constructions. So this again gives n to the 1 over epsilon kind of list size bounds, but there's more structure to this. And then the structure was used by something called subspace evasive sets, constructed by Dinur and Lovett. That improved the list size bound to 1 over epsilon to the 1 over epsilon. So it's a constant independent of n. We're going towards 1 over epsilon. And then Koparty, Ronzevi, Saraf, and Wooters in 18 showed that folded Reed-Solomon codes themselves without these subspace evasive set type modification have similar list size of 1 over epsilon to the 1 over epsilon. This proof was sort of slightly simplified and streamlined by Tamu, who had a similar list size bound of 1 over epsilon to the 1 over epsilon. And then finally, I had a work that improved this list size to 1 over epsilon square, again for folded Reed-Solomon codes themselves. And in an independent work around the same time, Chen and Zhang showed that the folded Reed-Solomon codes have the optimal list size of order 1 over epsilon, which is the best you can hope for. Okay. So at least in terms of list size, this result supersedes all of the earlier ones. and I'm going to talk about this one. I'm going to present a proof of this result, which is slightly different from the proof that Chen and Zhang gave, and it's somewhat closer to the expander-based proof for a similar property that we saw for optimal list size. So if you were in Madhur's talk on Monday, then you'll see some similar ingredients as that talk. Okay. So why do we expect a list size only of 1 over epsilon? The reason is something called generalized singleton bound. So for any rate R code, I can always find, let's say, 3 code words that agree in the first roughly Rn coordinates. So there are some 3 code words that agree exactly in the first R fraction. That's simply by pigeonhole because there are q to the Rn many code words. If we have these 3 code words, let me construct a receive word. Let's say these are code words H1, H2, H3. I construct a receive word with the same common value in the first half. For the second 1 minus R fraction, maybe use the first guy to construct the first 1/3, second code word here, and the third code word here. Okay. This is a received word. What we can see clearly is that for each of these, the distance is 2 over 3 times 1 minus R. There is no distance from the first R fraction. There is no distance from 1/3 of the remaining 1 minus R fraction. So for all of these 3 code words, the distance is at most 2 over 3 1 minus R, which means that as soon as we have radius 2 over 3 1 minus R, we cannot hope for list size less than 3. For any rate R code, there exists a Hamming ball that will have 3 code words with this radius. And so this is a bound that holds for every code. Our job is to design codes that actually gets close to it. So in the sense that design code with list size 2 up to 2 over 3 1 minus R or 2 over 3 1 minus R minus epsilon. And these results show, so this result will show something stronger, that even for a fixed list size like 2, you get the optimal threshold. If you keep pushing this idea, list size 2, 3, 4, so on, the thresholds will grow according to a 3 over 4, 4 over 5, and so on, until we approach 1 minus R. Yes. So there might be like a 2-factor away, but up to that, it's optimal. Yeah. So these all results are with a fixed list size.
Constant is off by 2 because of this. There is an epsilon inside
Right.
1 minus R, and there is epsilon from the ratio.
Right. Yeah, so that too is sort of artificial. You get for any fixed list size, there is the right threshold. You can approach it as closely as you want. Okay. Maybe I can use that side of the board.
You can't flatly achieve it also because of differential field size lower bound.
Right. So this slack version, right. Okay, good. Yeah. So here, what we want to do is actually list decodable up to some slack. And even for list size 2, if you don't have the slack, then you need a large alphabet. Is that correct? Yeah. Okay. You need an exponential size alphabet. What we are going to show is folded Reed-Solomon with polynomial size alphabets do all of this. So that slack there is necessary. Okay.
One slight caveat to that
Okay, but I think all of these results are also doing up to list size k. So the lower bounds do apply. Okay. Again, what these results show is actually something stronger, something called average radius list decodability. So what this means is that if we have some k plus 1 many code words that are all distinct, so h0 to hk are distinct code words, then the sum of their distances from any g, so there is a quantifier here, for all g, for all h0, h1, k, this has to be more than k times 1 minus r. The HIs are code words, they are distinct code words. And this implies list decodability because, I'm using k plus 1 of the code words. Yeah. So this means that one of these code words must be at distance more than k over k plus 1 times 1 minus r. Slightly ignoring the slack here. So if I take any set of k plus 1 code words, one of them must actually escape the Hamming ball, which means that the number of code words in the Hamming ball is at most k. Okay. So this implies list decodability. It's a stronger notion. We're actually going to prove this. Okay. And the proofs are actually going to be somewhat generalizations of distance proofs. So the most basic, like when we don't have generalized singleton bound, we just have the singleton bound. And then we want to approach the singleton bound that translates to distance of the code. And we all know how to prove the distance of the Reed-Solomon code. So this is the distance of the Reed-Solomon code, that if we have a rate R code, the distance of any two distinct code words is more than 1 minus R. This is actually equivalent to saying that for all G, H1 and H2, the sum of distances from any G is going to be at least 1 minus R. Okay, it's just a triangle inequality, but it's also equivalent. One side is triangle inequality, the other side you can just take G to be H1, for example. Okay. And how does the proof of the distance of Reed-Solomon code go? We look at the difference of the two code words. That's a low degree polynomial. And then it can't have too many zeros. Every agreement is a zero. And because it can't have too many zeros, there can't be too many agreements between two polynomials. If we want to prove this sort of inequality, so for k equals 1, this is distance. For larger k, we would want some sort of statement that talks about properties of 3 code words at a time, or 2 code words at a time. The property that we are going to use is called the folded Wronskian criterion, which says that, let's say I have some d polynomials. I have D polynomials. I arrange all of them into rows of a matrix. And on the second row, I put the polynomial, but changed a bit. So polynomial applied to gamma times x. And so on. I do this for D minus 1 rows so that this becomes a square matrix. So one thing you can quickly see is if these polynomials are linearly dependent, then the determinant has to be 0. Because some linear combination of theirs is 0, which means the determinant has to be 0. The folded Wronskian criteria says that there is a converse to this statement, that this is non-zero if and only if these polynomials are linearly independent. So this is just a statement about a few polynomials at a time, nothing to do with codes. Here gamma, okay, yeah. Gamma is the primitive element of a field. Of the field that I'm working over, or a generator. And it's only the converse direction that uses the primitive element property, yeah. Oh, okay, yeah, so I do mean the determinant of this, just to be explicit. Yeah, the determinant of this matrix as a polynomial. So because we are fitting in polynomials as entries, the determinant is also going to be a polynomial. And as a polynomial, it is going to be 0 if the polynomials P1 through PD are linearly dependent. Okay, so this at least gives me something that talks about few different polynomials at a time. I could try to use this for this sort of property with multiple code words at a time. Okay, so now let me go back there. Yeah.
Stronger notion than this probability. And
Right.
If you know that that is true, then you can't have more than k
Right.
code words in the ball around 1 minus r ball around any word.
K over k plus 1 times 1 minus r. Yeah.
Right. And then why did we?
Right. So that's just the notion. Now we are trying to look at how to get a code that achieves that. For k equals 1, the code that achieves that is Reed-Solomon. And now we are trying to see how to get it for larger k. Okay, so we are dealing with arbitrary g h0, h1 up to hk. And we want to get some sort of average radius list decodability property. First of all, by shifting everything, we can always assume that h0 is 0. We can subtract h0 from everything, and none of those distances will change. Similar to distance proof, where you always pick one of them to be 0. So let's say this h0 is always 0. Okay. So I want to use the folded Wronskian. I can do that easily when h1 through hk are linearly independent, because that's where the folded Wronskian kicks in. It's not clear why we should look at this, but if this were the case, then we can get that sort of average radius list decodability property, and let's see how to do that. In fact, I'm going to change this k to s. Okay. Let me draw all of these polynomials. So one modification that I need to do to my code to get here is fold the code. Where, let's say the evaluation points were all 1 gamma, gamma square, and so on. So we fold it, for example, let's say S things at a time. So that each symbol looks like F1 gamma. This becomes a single symbol. And then the next symbol starts from gamma to the S. The previous code word was of length capital N. The new code word is going to be of length capital N divided by S. For now, they are the same as. I'll change that later. And this new block length, I'm going to call little n. So that's the effective block length of my code after folding. The block length goes down. Okay. So I write down all of these code words and let me mark out wherever this agrees with G. So in each code word, there are coordinates where H0 will agree with G, there are coordinates where H1 will agree with G, and so on. Let's say these sets are A0, A1 up to AS. I can look at them as a column set. We can also look at them as a row set. And let those sets be B1, B2 to Bn. That's the number of coordinates we have. Okay. Okay. So my claim is that the first one is 0. Yes. Yeah, because H0 is always 0, so it will never be, yeah. So it can never be linearly independent. These are the sets where we have agreements. Yes, yes. It's an index of rows, yes. Yes, yes, yes. And these are actually going to be subsets of 0 to S. So if Bi is L, and this L is going to be something between 0 to S plus 1, right? For now, yes, I'll do the sliding window thing later. Okay. We have Bi equals L, then okay, maybe I just give a notation to this Wronskian. The Wronskian is the determinant of that matrix. Yeah, so for some Bi, yes. The Wronskian of H1, H2 up to Hs has so if one of these sets Bi has a lot of agreements in a row, then we get a root for the Wronskian with somewhat large multiplicity. Okay? And why is that true? Because if I just look at the Wronskian and write it down, 1x gamma to the 1x then because of this agreement, let's say there are two cases. Either all of the L agreements were after H1 through HS. In that case, in the matrix, I will get L many common columns. Because agreement actually is folded according to S symbols at a time. So agreement will mean that those columns here, when I substitute X equals gamma to the I minus 1S, those columns will just become equal. So if I have L many columns that are equal, if you have any two columns equal, you get a root. If you have more than two columns that are equal, you get a root with multiplicity there. You can just look at the determinant and it will continue to vanish even after you look at the derivative. And the other cases, if you have 0, in that case, any L minus 1 will already be 0 and will have multiplicity L minus 1. Okay. Either way, whenever Bi is L, you get a root with good multiplicity there. And the multiplicity is driven by what is the size of Bi here. This is a non-zero polynomial and its degree is going to be what was the degree of each of these polynomials? Well, when I started, I had capital N many points and the rate was capital R. So the degree was actually Rn. And then determinant is going to make the degree go up by a factor of S. So the total number of roots cannot be more than this degree, which means this is the size of Pi, but if I actually wanted to look at this, then this is simply whatever is left over. So whatever is not marked out are the differences. So I marked out all the agreements. Whatever was not marked out is going to contribute to these differences. So that's why S plus 1 times N is the total size of this matrix minus the term here, minus summation Bi. And then we can use this bound. This will give you right. Where I'll at some point use that little n is capital N over S. It's off by this little s factor, otherwise I would be very happy. But that turns out to be sort of artificial. You can remedy this. You do pay a bit more. So instead of folding up to S, what you do is you fold up to a different number, M, which is larger than S. Here, instead of getting one root, you'll start getting M minus S plus 1 many distinct roots. And this capital N is actually Rn times M times S. So if you do this change, then for M that is large enough compared to S, these things will cancel. And you'll recover this. S will tend to 1. So formally, you would choose M to be roughly S over epsilon if you want there to be an epsilon here. Okay, but these are things that we have known for a while. But okay, note that this already means that the list is contained in an affine subspace. Because if the list was more than affine subspace, the dimension was more than S here, then I could choose some S plus 1 linearly independent things and still get and sort of violate the property that we have just proven. Right? If the list had dimension more than 1 over, the list had dimension more than S, then I would choose a basis for that space. All of them will have less distance to G. And then the sum bound for the distance will no longer hold, that we have just proven. So the list must be contained in a dimension S subspace. And when you choose S to be 1 over epsilon, you get that the list is contained in 1 over epsilon dimensional subspace. So this is roughly an analog of Guruswami's result from 2011. And his result also gives an algorithm to find a basis for this subspace. That is not clear from here, but at least combinatorially you get this. So the next question is, how do we get to the optimal list size? And really what I want to do is not worry about this linear independence, but talk about distinctness. If I can make all of this argument work with just distinctness, then I would get optimal list size, right? But that's tricky because folded Wronskian, the way we defined it was precisely about linear independence. So how do you bring in distinctness? And it turns out that you've kind of already done most of the work. Again, let's go there. How much time do I have? Okay. So let me think of this set of code words that I'm dealing with as capital H. And H0 is again 0. We saw that if these were linearly independent, then Wronskian will help us get the right result. Now we want to deal with the case when these are just distinct and not necessarily linearly independent. Let me partition this set into, I always treat H0 separately. So I partition it into P parts, where P is the rank of this set. Rank of the later S of them, because first guy is 0. I don't want to deal with that. So it has some rank. That rank I'm calling as P, and we want to deal with the case when P is less than S. If P is equal to S, we are already done. So P is less than S. I'm going to partition my entire set of code words into P parts such that if I look at any tuple that I draw from F1 from H1, F2 from H2, FP from HP, then these are all linearly independent. Okay? So, in other words, everything in this Cartesian product is a basis for the space. This you can easily do by looking at, so let's say F1 to FP were a basis without loss of generality, then HI could just be all H in H such that you pick a basis, write down coefficients, and partition it according to the last non-zero coefficient you see. That's going to give you a set like this, where each tuple that you draw from the Cartesian product is going to be linearly independent. It's just very basic linear algebra. Yeah. Sorry?
What do you call F chain? That's like page one.
Yeah, so here I'm calling it F1 through FP because I want to draw them arbitrarily from this set HI. Yeah, but like without loss of generality, you can think that the basis was first P elements. Yeah, but whatever are the basis that you have picked. Or you can also greedily construct this, that either a new thing is a linearly independent guy, or you put it into one of the earlier ones. Okay, so that's a partition of this distinct set of code words. And now I'm going to use two facts. Okay, good time to not erase this. The Wronskian as written seems like a property of P1 through PD, the D polynomials, but it really is not, because you can take linear combinations of these things and it will still be the same polynomial that you get up to some constants. And in fact, it is a property of the subspace that they span. It's invariant under the subspace. Okay. So for any of these tuples that I draw, the Wronskian is actually going to be the same, right? So I could have drawn a single tuple from H1, H2 up to HP and did the argument there in the linearly independent case. And I would get something based on zeros of the Wronskian. I could do it again for some F1 prime and other things same. And again, I would get some sort of bound based on the linear independence. But if you notice, the Wronskian of these two tuples is going to be the same. So these are going to be roots. In both cases, we get the roots of the same polynomial. So we can take the union of agreement sets here, which is to say, maybe I'll just erase that. Now I draw these, there's always an H0 here, which is all 0. Now I draw P slots here, and these slots I will fill with elements from H1, whatever went to H1, or slots from whatever went to H2 and so on. And previously I had drawn these sets A1, A2, AS there, which were based on agreement between G and H. But now I can actually take the union of agreements between everything that I see in H1. So A1 is going to be union of agreement between G and H, where H goes over all of H1. And even if I take the union, I can do that argument because the Wronskian is shared. I can count the roots for that same single polynomial. Okay. So what we get is, and here, when we move from distances to agreement, now we have a union of agreement that is going to correspond to the number of common errors here. The union of agreements corresponds to intersection of error sets. So if you do this argument, you will get so note that if we just did the argument individually, this is what we would get always. For any F1 through FP tuple, we could do the linearly independent argument and we'll get something. But this is saying something stronger, that we get it for common error locations for all of them. So delta GHI, to be precise here, is the set of all coordinates where G differs from every code word in HI, not just one of them. Because we took a union, if even one of them was an agreement, then we could count that root. Okay. This is going to be my first inequality. The second one, I'm just going to strengthen the base case. So we have this k equals 1 case when we have just distance. This is really triangle inequality, right? When we do triangle inequality, we are counting the common error locations twice, right? The way we do triangle inequality is H1 and H2 differ in, let's say, this position and this position, then G has to differ either here or here. So the total has to be more than 1 minus R. But if G differs in both the positions, I've double counted that. So I can add that term back. It's not a notation I've defined formally, but both H1 and H2. So for each of these cases, I will actually have this extra dangling term that we were not using until now. And then this extra dangling term can be hooked to this. Okay, let's just finish this last part. So I started with S things. I partition them into P parts. Right? For each of these, I can use induction, but with the extra dangling term. So technically, I would have to strengthen my induction, but you can believe me that that can be done. This term here, this is going to be less than S many things, so I can use induction here. This is the dangling term that I talked about. It's the extra term that we have introduced from the triangle inequality, starting from there, but it really is preserved throughout the induction. The first term, if I sum, is just going to become S minus P times one minus R, because these HIs are a partition. The second term is summation delta GHI. And that's where I use this fact that we could do the Wronskian argument for common error locations. Take this part and this part. That would give you, this is also. We lost some S minus P. You regain that in the by looking at those P partitions together. That's it. Again, technically speaking, I would have to strengthen this statement also to get the extra dangling term for the induction to work out, but that can be done. Okay. So once you prove the linearly independent case, distinct case kind of follows from a similar argument. Quickly mention a couple of open things or future directions more like. I mean, one of them is just folded Wronskian is a criteria for checking linear independence. What is the criteria for checking distinctness? And for points, we have simple criteria like van der Waals determinant, etc. You can try to use that for polynomials directly. And can you give a more direct proof instead of first proving it for linearly independent case and then trying to do this extra step? The second is algorithms. So algorithms, like I mentioned, actually go via this step. You can get a basis for a subspace that contains the list, and then you try to prune that basis out. But really, we might want to algorithmize the distinct version of the proof, where you get directly a set of code words instead of a subspace of code words. And yeah, I mean, there's this excellent exposition by Prahladh, Ramprasad, Mrinal, Garg, and Shankar. You should check this out. I mean, that proof is quite simple, and it's not too different from this one. Okay.
Thanks a lot. Any questions for Shashank? Maybe the next speaker can set up also.
Sorry? No, distinctness is throughout. Like the whole sum inequality only makes sense when you have distinct code words. If you don't have distinct code words, then you won't get such strong lower bound on the sum of distances. You provably won't, because you can choose just G to be close to one of them. And if all of them are same, then you're not really using different code words. I mean, I use distinctness all over the
triangle inequality in the base.
Sure, yeah. Yeah, but I use distinctness all over the place. Yeah. Yeah, I'm not sure. So this is slightly different proof. Probably a little simpler, arguably. But yeah, I'm not fully sure how those things get connected.
Okay, no other questions? Right, thanks again.
Yeah.